just finished the kinetic measurements, 4 kinetic measurements, and last time we have discussed about potential static method and the galvanostatic method. So we have to talk about the potential metric method and AC impedance analysis. Well, today we are going to talk about the potential metric method, and then on Wednesday we're going to discuss about the AC impedance spectroscopy. Okay. Last time we have potentiostatic technique and galvanostatic technique, and for all of this, just for measure the kinetic parameters, especially the diffusion coefficient of electroactive species, in cathode, okay? And the cathode is supposed to be a mixed conductor. Means it should be electronically conducting and ionically conducting. But the diffusion coefficient that we are concerning is the things where for example, if you do the discharging, for the discharging reaction, you're going to have electrons from the backside of the cathode, and here you're going to reduction reactions like that, and then this neutral lithium is going to diffuse inside the cathode material due to the concentration gradient, and then that's a fixed law. This diffusion coefficient is the diffusion coefficient that you try to determine. Okay? So if your cathode material has a high diffusion coefficient, then this cathode can take a lot of lithiums, because the surface concentration from the Nernst equation says the potential of this system is activity of electroactive species at the surface, that is at x equal to 0. So if you have a high diffusion coefficient material, it means that the lithium, which is going to be at the surface, is going to be diffused into the electroactive species very fast. So that with the insertion of the lithium into your material, your voltage is not going to go down quickly, because the lithium is going to be diffused inside, okay, according to the Fick's law. So you want to have high diffusion coefficient materials as a cathode in order to have a high capacity, okay? So it is very important to determine the diffusion coefficient, and in the potential static method, you apply the constant voltage, which the voltage is determined by this fact, okay? And then you monitor the current change, okay? And you solve the fixed second law, fixed second law, then you end up with some equation which is a series solution, but you can approximate the results, especially the current that you monitor is going to be Q over L D and pi t skewered for a short time. So if you monitor the current change, then you can determine the diffusion coefficient according to this equation at the early stage of the experiment. Okay? And in the galvanic static method, you apply the current and then you monitor the voltage. And by solving the fixed second law, diffusion coefficient in this case can be set IBVM over GFS, that is the surface area. Okay, and then dE versus d delta over dE dt square, things like this, okay? And this is the slope in the coulometric titration curve. And this is the voltage change that you monitor in the galvanostatic method, okay? So basically you can determine the diffusion coefficient. Of course, this is the results at the early stage, where the dE over d delta is linear, okay? Then you can determine the diffusion coefficient. And the last time I showed you the measurement of the diffusion coefficient at each concentration of the lithium in the lithium hexatungstate electrochromic film. And you can see a lot of diffusion coefficient data here. And this many diffusion coefficient can be determined within it's a matter of a day or two experiments. So we think this is a very powerful method. Now, the third one that today we are going to talk is the potentiometric technique. Okay, that is number 3. Potentiometric method is nothing but it's basically potentiostatic method, but you are going to apply the voltage very short period of time. Very short period of time. You can apply the current or voltage. Either will do. And then you monitor the change in voltage or current in that short period of time, and that is going to be called the potentiostatic or potentiometric method. And here in this case, the solution of the fixed second law is going to be, that equation is going to Q over ZF as pi d t square root and exponential minus x squared over 4 dt. Okay? For time is very much shorter than characteristic length, diffusion length. Okay, that is for the potentiometric method. And then you are going to have a boundary condition like with these three boundary conditions, you can basically solve the fixed second law partial differential equation. And solution is going to be duration of the current pulse or the voltage pulse. Okay, CS and you are going to plot of course, in these equations, Q is the current which has been passed during the experiment. So in this potentiometric method, we have a couple of advantages. No current loss, current flow during measurements. We just use the pulse, okay? No ohmic loss. In electrolyte electrode interface. And irreversibilities of charge transfer reaction. The charge transfer resistance or charge transfer reaction is related to the combination of this lithium ion and lithium electrons to form a neutral lithium. Okay, here the resistance that at the x equal to 0 is going to be called the charge transfer resistance. That is the charge transfer resistance. And this is not included in the IR drop, internal resistance, okay? So irreversibilities, any irreversibilities of charge transfer reactions or the polarization due to ionic transport. In the electrolyte. These two things can be eliminated in this potentiometric method. Eliminated. Okay, in this potentiometric method. By the way, the results that I showed you in my PhD thesis, this results was obtained by galvanostatic method. We make the coulometric titration curve separately. That is the thermodynamic equilibrium values. So we spend a lot of time to form a coulometric titration curve of this potassium hexatungstate materials with respect to the lithium concentration separately, and then we carry out the galvanostatic technique at each lithium concentration in the potassium hexatungstate. And at each point, we determine the diffusion coefficients according to that equations that I showed you in the galvanostatic method. Okay, so if you are interested in kinetic measurements of materials, this electrochemical technique is very powerful to measure the kinetic parameters, especially the diffusion coefficients, very precisely. Okay. The one thing that you have to be careful is that the equilibrium state is very, you should not wait for a long time for the equilibrium. This electrochemical technique usually carried out at room temperature. If you elevate the temperature, then your electrolyte is going to evaporate and side effects may happen. So usually you calculate or you measure the experiment at room temperature. So the kinetics is very slow at room temperature. So what you do is you make a cathode material in a thin film form so that the distance to be equilibrated is very short, like less than 1 micron. Then it can be equilibrated in a reasonably quickly so that you can exercise this technique very easily. Okay? In a bulk material, usually it takes a long time to be equilibrated, so it is very hard, difficult to use this electrochemical technique. But if you use the salt as an electrolyte, then usually the salt can be kept in the temperature range of 400 and 500 degrees centigrade, in around there. So if you can use the salt as an electrolyte, then you can carry out this experiment at the elevated temperature as well. Okay, I'll see you on Wednesday to discuss about the AC impedance spectra, which is a really powerful method to differentiate each reactions at the different places in your batteries, electrochemical cell. And it's very powerful because it can distinguish the reactions at the different places. Okay, I'm sorry, but I'll see you on Wednesday. Okay.